Hey everyone. So in this video, I just wanted to set up a problem. This is going to be a class participation type problem. I'm going to set it up and then have you guys try to finish it so I can just see where everyone's at with rotation. And then I'll be putting another video out. We're going to start talking about fluid mechanics. If you look at the syllabus, we should be doing material science or something like that. We're going to skip over that and just start with fluids. But first, let's just take a look at this problem. So, we when we first talked about kinematics and forces, translational kinematics, we looked at the Atwood's machine, which is what I've drawn here. We have a pulley, and then we have a mass hanging from each side. And originally, when we looked at this problem, we assumed that this was a massless pulley and that it has no friction as it starts spinning. So in this case, we're going to assume that this actually still has no friction, but we still have the mass of a pulley now. And we know that as these start to move, we have conservation of energy. So as we release some of the or convert some of the potential energy from gravity into kinetic energy, and these boxes start moving, and as we could see here, mass 2 is much larger than mass 1, so we could assume that mass 2 is going to start dropping down because this pulley has a weight to it. It's also going to have some sort of energy we have to consider. So this system's going to behave a little differently than what we saw when we ignored the pulley. So if we kind of just think about where all of our forces are at in this, we could see that we end up with, if we look at mass 1, we have this force, mass times gravity, downwards, but now we have this tension upwards, tension 1, that's got the force that is getting this pulley to rotate. Well, we're going the other way. So, but if we just think of it as generically, this is going to be opposite of our force. And then we have our force 2 from mass 2 times gravity. And then we're still going to have this tension in the opposite direction of this rope pulling back on it. So tension 1 and tension 2 in this case aren't going to be the same value. So we need to consider both of those. And this should make sense because if we look at it, our tension 1 and our tension 2 are both out at the rim of this pulley. So if they were the same value, this system wouldn't move, right? Because we'd have the same amount of torque in opposite directions being applied to this pulley, and we wouldn't have any motion. So let's just set up some equations and see which direction we could go in. So looking at mass 1, we could set up the equation saying that we got the force downwards. I'm making this a positive because it's trying to rotate the wheel in a counterclockwise direction. So that would give us a positive angular acceleration or torque. They're going to point in the same direction. And so our torque or tension 1 is in the opposite direction of this force, so I gave it a negative. And then, of course, this is our sum of forces, and that's going to equal our mass times acceleration. And we're only looking at mass 1 here. So we could do the same thing for mass 2, only this time it's on the opposite side of the pulley, so our signs are going to switch. Our tension we're going to call positive because it's in the counterclockwise direction, and we're calling our force 2, this mass 2 times gravity, a negative because it's trying to spin the pulley in a clockwise direction. And then that is equal to mass 2 times acceleration. Well, we only have 2 equations here, but we have 3 unknowns. We don't know acceleration, and we don't know tension 1 and tension 2. So if we look at the pulley, we could come up with a third relationship because we know that torque equals I alpha, the moment of inertia times angular acceleration. And so all we need to do is, just like when we solve F equals ma, where we summed our forces and we get our mass times acceleration, we need to sum our torques, and that's going to equal our moment of inertia times angular acceleration. So our torques, we have this torque 1 at our radius r, because torque is our force at our magnitude of torque is the magnitude of our force and times the magnitude of our radius. So, and it times the sine of theta, but here we have it as 90 degrees, so sine of theta is just 1, so I didn't write that. But anyways, so our first torque is this torque from tension 1 times R, and then in the opposite direction we have tension 2 times R. And then in this case, we're going to represent our moment of inertia, Ri, as a disk. If we look at our moment of inertia table, we're going to use letter F, I think that says, yes, a solid cylinder. So it's just 1/2 mr squared. So we could plug, oops, sorry, I didn't realize the video was off the screen. So looking at our torques, we have tension 1 times the radius minus tension 2 times the radius, and then equals 1/2 mr squared. That's just our moment of inertia for a disk. And then we're multiplying that by our angular acceleration. But now we still have the problem that we don't know acceleration, we don't know tension 1, we don't know tension 2, and now we don't know our angular acceleration. So now we have 4 unknowns and only 3 equations. But we know we could represent our angular acceleration in terms of our acceleration at some point, our tangential acceleration at some point on this on the pulley, and that relationship is just that alpha equals our acceleration over or divided by our radius. So basically, I'm going to leave it here. You're going to try to use these 4 equations and come up with our acceleration of this system. And after everyone gets it turned in, I'll do a follow-up video where I solve this. So once again, you're trying to solve for acceleration. We're using these 4 equations. This is just the relationship between our acceleration and angular acceleration. This is our torque form. It's summing the torques to get our angular acceleration. And then these are just Newton's second law, F equals ma. So if we combine all these, we should be able to solve for acceleration, because we have 4 unknown values and 4 equations. All right, so I'll be posting another video shortly, like I said, about fluid mechanics. Let me know if you guys have any questions. For participation, don't worry about getting it correct. I just want you to attempt it without looking up the answer online and just sending me that. I don't really care what the answer is. I'm more or less evaluating if you're able to do this type of problem. Anyways, I'll talk to you guys soon.